Good afternoon, everyone. Good afternoon, everyone.
Good afternoon, teacher.
Sorry, I have a toothache. It's disturbing me. But I'll be fine. So let's get started with work done during a diabatic process. The work done during a diabatic process. If you consider an ideal gas, of any moles enclosed in a vessel at a pressure P, if the volume changes by a small amount, that is delta V, then from the small change in work done, it will be equal to P times the small change in volume, whereby dW is equal to PdV. Now, if the volume changes significantly, when we say it changes significantly, then we can see that it has definitely changed, like from V1 to V2. Then total work done will be the integral from 0 work done of dW is equal to the integral from V1 to V2 of PdV. So the work done will be the integral of P dV from V1 to V2. But for adiabatic processes, PV gamma is equal to a constant. You can call that constant K, meaning P would be equal to K out of V power gamma, which is the same as K V power negative gamma. Now, when I substitute that P up there into work done, I'll have work done is equal to the integral of K V power negative gamma V1 V2 integrated with respect to V, whereby when we integrate this, we shall have K of V power 1 minus gamma divided by the new power, which is 1 minus gamma. And this is going to change from V1 up to V2. Remember, if you're integrating, the power has to increase by 1. So this would have been KV power negative gamma plus 1 divided by negative gamma plus 1. That's how it comes into this. So when you simplify it, it becomes K of V2 power 1 minus gamma minus K of V1 power 1 minus gamma, all divided by 1 minus gamma. But still, in adiabatic processes, P1 V1 gamma is equal to P2 V2 of gamma. And this is equal to a constant K. So I can substitute for K, give me work done is equal to P2 V2 gamma times V2 of 1 minus gamma minus P1 V1 of gamma times V1 of 1 minus gamma divided by 1 minus gamma. You can see that the gamma will die off and I remain with P2 V2 minus P1 V1 over 1 minus gamma. Also, for an ideal gas, PV is equal to a constant, which is N RT. We are assuming temperature is constant. So it means P1 V1 is equal to N R at temperature T1. Then P2 V2 will be equal to N R at temperature T2. With that, when you substitute, you'll have work done is equal to NR T2 minus NR of T1 divided by 1 minus gamma. So finally, work done is equal to NR into T2 minus T1, all this divided by 1 minus gamma. So this is the expression for work done in terms of temperature, in terms of the ratio of molar heat capacities, and in terms of the molar gas constant R, and in terms of the number of moles N. So that is the derivation for work done in an adiabatic process. Someone has a question on that, you raise it. Now, some of these examples of adiabatic processes, they set the numbers with an illustration of sketching the graph. They can ask you to sketch the graph to indicate the process. So, an example, 1 kilomole of an ideal gas is initially at a pressure of 1.0 times 10 power 5 pascals at a temperature of 25 degrees Celsius. It undergoes a reversible adiabatic expansion to twice its original volume. Followed by a reversible isothermal compression to its original volume. One, sketch graph for the above process on the same axis. Then two, calculate the final temperature and the pressure of the gas. Then three, find the work done during adiabatic expansion and isothermal compression. So that's our number. It reads 1 kilomole of an ideal gas is initially at a pressure of 1 exponent 5. And the temperature initially was 25 degrees Celsius. It undergoes a reversible adiabatic expansion to twice its original volume, followed by a reversible isothermal compression to its original volume. Sketch the graph. Now that place is small. Let me use this place so that I can have a clear big graph for you to interpret it. Remember, in a adiabatic process, heat is not allowed to leave or enter the system, but the temperature can change. Likewise, also the pressure can change. At the same time, also the volume can change. But the graphs of temperature look like this. So this was the initial temperature T1. Then they said it undergoes initially, if initially this was the volume, had a pressure P1, which was initially here. Then the gas undergoes a reversible adiabatic expansion. So initially it had a volume V1. Then it was expanded to a new volume, which is V2. So it was expanded to a volume V2, and then it attained a new temperature T2. Then they said it was reversed back to the same volume. So on reversing it back, let me use another pen here. It comes back like this. It comes back up to this volume. But at that volume, it's going to attain a new pressure, which is pressure P2. So that's how the graph looks like. So we expanded it, that is expansion. This is adiabatic expansion. Then this second one is adiabatic compression. Okay. But also there is a pressure we attained here, which I forgot to mention. The pressure at this point is a different one. Okay, let me call this one pressure P3, the final pressure. Then let me call this one pressure P2. But the volume V1 is V. When we expanded it to a new volume, it became 2V. So I can have this process labeled A, B, up to C. So AB is what I've called adiabatic what? Expansion. Then BC is what I've called adiabatic compression. When you're compressing the liquid, the volume reduces. I mean the gas, the volume reduces. When you're expanding the gas, the volume increases. And remember, I told you that if you look at gas jars, the gas we used to cook at home, that gas is a compressed gas. When a gas is compressed, it changes state, so it becomes a liquid when the gas is overexpanded. I mean, compressed. That's why when you shake the gas jar inside, it sounds like it's a liquid. But when you turn on the gas, it comes out as a gas. So you're increasing the volume. So temperature T2, the initial temperature was 25. So T1 is 25. T2 we don't know. P3 we don't know. But this T1 is the same as 25 plus 273. When you add, you get 298 Kelvin. Pressure P1 is 1.2 times 10 to the power 5 pascals. Then V1 was V, while V2 has been doubled to 2V. But have this in mind. When they say adiabatic expansion, the volume increases, but the temperature reduces. When they say adiabatic compression, the volume reduces and the temperature rises. Okay? Then for isothermal expansion, the volume increases and the temperature remains constant. That's why for isothermal, the temperature is along this line, which is BC. The temperature did not change because it was an isothermal process. While it moved from A to B, because it was an adiabatic expansion. Sorry, this was not an adiabatic compression. It was an isothermal compression. You know, my head is not so steady. Because it is occurring at a constant temperature. This is isothermal compression. It is occurring at a constant temperature, this one. Which temperature is T2. This one was an adiabatic expansion. Okay, so with that, the first question wants us to find what? We have sketched the graph. Secondly, calculate the final temperature and pressure of the gas. From T1, if I consider AB, T1 V1 gamma minus 1 is equal to T2 V2 gamma minus 1. I can find T2. T2 will be T1 times V1 over V2 power gamma minus 1, which will give me 298 times V over 2V power 1.41 minus 1. The V can die off. Calculator, when you compute, what do you get? Press the calc and give me the answer. You're computing T1 is 298 times 0.5 power 0.41. That will give us the final temperature. It's an adiabatic expansion. We should press the calc.
224.
224.28 Kelvin. So if the answer is asked for in degrees Celsius, you subtract off 273 Kelvin. Then for case 2, the temperature is remaining constant because it's an isothermal expansion, compression. So at a constant temperature, we would have AB being equivalent to P1 V1 of gamma is equal to P2 V2 of gamma. Because temperature is constant, they're asking us for the final pressure. So we need to find pressure P2. P2 would become P1 times V1 over V2 power gamma. The initial pressure was 1.0 times 10 power 5 into V over 2V power 1.41. Did I give you that gamma was 1.41? I forgot, gamma was 1.41.
No.
So when you divide off and press the calc, what value of pressure P2 do you attain? Pressure P2 is going to be 1.0 times 10 power 5 times 0.5 power 1.41. Press the calc and get the answer.
37,000
pascals, right?
at 3.76 times 10 to the power 4.
Power 4, not?
Yes.
Now, they're asking us for the final pressure. The final pressure is attained between B and C. So the final pressure is at C. Now, because temperature is constant, that is an isothermal change. Isothermal change occurs at B, where PV is equal to a constant, meaning P1, V1 is equal to P2, V2. P1, oh no, not P1. This is now P2, V2 is equal to P3, V3. But V3 is the same as V1, which is the same as V. So we shall have 3.7 times 10 power 4 times V2, which is 2V, is equal to P3 times V. I can divide both sides by V, and I will eliminate the V. Therefore, P3 would become 7.4 times 10 to the power 4 pascals. Then the last part wants work done. Work done during what? During adiabatic and isothermal compression. Adiabatic, substitute for me this one. R is the molar gas constant. The value of the molar gas constant R is 8.31. The number of moles were 1 kilo, which is 1 times 10 power 3. Gamma, you know, substitute and get for me the work done under adiabatic expansion. Then during isothermal expansion, isothermal compression, work done, we derived it was nRT log to base E of V1 over V2, which would be work done is equal to nRT of natural log over half. It's natural log over half because V1 is V, then V2 is 2V. So when you divide the V, so you substitute both of them. And the isothermal is occurring at what temperature? The temperature we got as T2, which was this one. So get me that work done, because I don't want to wrap the question. You might have not copied the question. So substitute for me that and get me the answer. What answer do you get? For adiabatic?
1.49 exponent 6.
Then for isothermal, hope you know how to press natural log on the calc. Natural log on the calc is where we have, it is ln. You have it there, I think. For isothermal, what do you get? You're getting a negative, eh?
I'm lost.
I was saying to get this work done for the isothermal, the isothermal occurs at a constant temperature, which was T2. Which temperature T2 we got? 224.28. R is 8.31. Number of moles is 1000. Natural log, V1 was V, V2 was 2V. Those two, the V's divide. That's how it gets to a half. So substitute here and get the answer. For work done under isothermal. Negative 1.2, I mean 129.703. Yeah, the negative comes because of that natural log over half. Because the reason why it's negative, because it is reversible. We are doing the reverse of that work. So it's taking us back to where we were. So it's okay. So we have this other number. That's the sketch. The first question is to interpret the graph. So the first question is to interpret the graph, assuming temperature T1 was 310 K and the pressure P1 was 1.1 exponent 5. You can try to see what is going on and describe at least AB. Someone interpret for me what is happening between A and B. Now, when you look at that, the graph of temperature T1 is below the graph of temperature T2. Now, at A, we're initially at a temperature T1. So the gas was initially at 310 Kelvin. Yeah? And at a pressure of 1.1 times 10 power 5. It undergoes an isobaric process. You know, an isobaric process, we said, is a process where you have a constant pressure, where the pressure does not change. So it undergoes an isobaric process to twice its volume, because they have said V1, if it is V, then V2 is twice of V. It undergoes an isobaric process to twice its volume at B. Then it undergoes a constant, at that instant, it undergoes an isovolumetric process. Isovolumetric, it means it has a constant volume. So it undergoes an isovolumetric process to come down to C. And the temperature would fall to temperature T3. Yeah? So when it undergoes an isovolumetric process, it does so until the pressure reduces to P2. Then it undergoes an adiabatic compression until the pressure rises up again to P3 and the volume goes back to its original volume V. So they're asking you to summarize that. So in summary, you can say a gas at 310 Kelvin and a pressure of 1.1 exponent 5 pascals undergoes an isobaric process to twice its original volume. It then undergoes an isovolumetric process until its pressure is 2.4 times 10 to the power 4, because they say that is what P2 is. It then undergoes an adiabatic compression to its original volume. So have we finished writing that? I'm not feeling so well, so I don't want to write a lot. So I was saying a gas at 310 Kelvin and a pressure of 1.1 exponent 5 undergoes an isobaric process. Or if you don't know the word isobaric, you say it undergoes a constant pressure to twice its original volume. It then undergoes an isovolumetric process or an what? Or a constant volume process. Until its pressure is 2.4 times 10 to the power 4. It then undergoes an adiabatic compression to its original volume. So that's the description of the graph.
Teacher, if you don't mind, could you please repeat the last paragraph?
It undergoes an adiabatic compression to its original volume. Got it?
Yes, teacher, thank you.
You're welcome. So in the beginning, if you consider AB, it's occurring at a constant pressure, whereby you can use Charles's law, which is V1 over T1 is equal to V2 over T2. So volume 1 was V, temperature T1 was 310, is equal to V over temperature T2, which we don't know. T2 is equal to 620. So when you consider BC is occurring at a constant volume. P1 was occurring at a temperature T2. Then P2 is occurring at a temperature T3. So when you substitute, we shall have 1.1 over T2, which is 620, is equal to P2, which is 2.4 times 10 power 5 divided by T3. What answer do you get? You get 1 point?
1.35.
1 point what?
1.35.
135 or 1.35?
1.35.
Supposed to be 135.27.
Yes. So that comes about after converting.
Excuse me for Guys, I'm sorry, I have a concern. Seems my fever is really high. What else have you got? Hello? What else have you attained?
Teacher, I was saying 1.35, but this is what you've given us, 135.2.
So it's the same, eh?
Okay. I was asking how does it get to 135, please?
Hey, this one is in Kelvin.
Yes, it's already in Kelvin.
Then the other ones from CD is an adiabatic compression. Eh?
Yes.
CD is adiabatic compression. It is occurring with change in temperature and volume. So we shall use TV gamma minus 1 is equal to a constant, whereby we are moving from a temperature T3 and a volume V2 power gamma minus 1 is equal to temperature T4 times V1 power gamma minus 1. This can make T4 the subject, which is T3 into V2 over V1 power gamma minus 1, whereby T3 we have already attained it as 135.27 times 2V over V power 1.4 minus 1. And you press the calculator to find T4. Then we can also find pressure P3 using PV gamma is equal to a constant, whereby you would come from P2 times V2 power gamma is equal to P3 times V1 power gamma. Then P3 would be P2 times V2 over V1 power gamma, which is P3 into 2V over V times gamma. Therefore, you would get P3 times 2 power 1.4. Then you substitute and find the pressure. I'm going to let you finalize with this. I'm not feeling well right now. Then for the last part, total heat energy is equal to NCP delta T. They want to find CP. So the change in heat energy would be equal to, the change in temperature. Change in temperature would be 620 minus 310, which is equal to 310 Kelvin. From PV is equal to nRT. N is going to be equal to P1 V1 over R T1. So you can find N, which is going to be 1.1 times 10 to the power 5 times V over 8.31 times 310, which will give us 42.7 V. Because we don't have the value of V, so we shall express the number of moles in terms of V. They wanted it, heat supplied at a constant pressure. So when you get the number of moles, then substitute up here. And then you get everything you want. So finalize that. I'm going to send the number. You try out. Otherwise, I need to take some fresh air. Finalize as I take my fresh air.
You guys, what are you getting?
Guys, are you still there?
Yes.
Hey, what answers have you got? Three what? Three, I have Nachibugu has 3, 8, 7. For what? For the pressure. For the last one.
Yes. Yes.
No. You know, I've handled that number when I'm not sober. I think I'm truly sick. I have to first go to hospital. Let me see if I'm done. If I'm well, I'll teach the lesson. If I fail, I'll communicate the night lesson. I'm not feeling so good.
Okay.
You pray for me to be fine by night. Okay, let's stop here.
Get well soon. Bye.